pulled at a constant speed by a force at an angle to the surface, and we have friction. How many forces are working on this object? Close. Not 3.5. 4 forces. All right, what are the 2 easy ones? You bet. So we have our gravitational force, we have our normal force. Okay, what else? We have a friction force, and then I heard somebody say the other one, the applied force. Okay, so the applied force is coming up this way. We'll just leave that F. We'll use that F there, F applied. So our free body diagram looks like this. Now we don't know the lengths of these vectors. The whole purpose of a free body diagram is just to identify the forces working on an object. But obviously we're going to take it a step further and really figure out what's happening here. So I am purposely drawing the axis this way. So we have our positive y, we have our positive x. I'm drawing it this way because I have my normal force, my friction force, and my gravitational force are all up, down, left, right? So this is helpful because 3 of my vectors can fit perfectly on here such that they don't have components. You are more than welcome to turn your axis, and we can make this the positive y direction, but that means for 3 other vectors, we need to draw the x and y components, and it gets really messy. So not always, but most of the time, I purposely draw my axis to contain most vectors so that they're on there and they don't have components. So I'm going to purposely draw my applied force vector, because if we have the vector that has 2 directions, it makes it really easy to draw the components. So if this is my vector, then it's coming out this far in the x direction, and it's going up this much in the y direction. So this is my applied vector, and that's my y component of the applied vector. Here is what component? The x component of my applied vector. All right, so let's go back to the problem and read this. The object is pulled at constant speed. Why is that important? Because we know the net force has to be 0. So we know the net force equals 0. Now, if the net force equals 0, let me give you a hint, you guys. If it's equal to 0, it's not saying the x component is equal to 0 or the y. It's just saying the net force is equal to 0, which means in both directions, the magnitude of the vectors, or the sum of the vectors, have to be equal. Okay? So if that's the case, let's take a look here. What other vector is going to be on my x-axis? Friction. And what do I know because the net force is 0? This is my x-axis. Because the net force is 0, what do I know about the relationship with friction and my x component of my applied vector? They have to be the same. Excellent. So I know that my friction force has to be equal to the x component of my applied force. So I'd come over here. I would try to measure this out a little bit. So I know these have to be equal. And this is my friction vector. Good? All right. This next part's a little tricky, so I really like this problem for what it's demonstrating. Now, if a box is not going through the surface, we have gotten into the habit of saying, oh, the normal force and the gravitational force must be the same, right? Because otherwise it would go through. But we have a different situation here, and that different situation is my normal force is not my only upward force. What's my other upward force? my applied force in the y direction. So the y component of my applied force is also creating an upward force. So here's the thing, if my net force is 0, that means the sum of all my y forces upward have to equal the sum of all my downward forces. Well, here I have two upward forces. I have a normal force and I have the y component of my applied force. And together, those equal my gravitational force. If this happened to be more, then the object would be floating. It would move upward in the air. Okay? So, what I have here is, I'm going to purposely make this guy small. So I'm going to call this my normal force. And then we need to add these two. So it's going to be about this much. So if I add these two vectors, this is my gravitational force. Okay? So what happens is the sum of these two is equal to the gravitational force. These two are equal. All right, now is my object at rest? No. It's just not accelerating. So it's in motion, it's just not accelerating. So that's why these are all equal. Okay. Last example. All right, what do we know about this problem that's going to be really helpful? We know that this is motionless. This one, the circle, is really important because there are forces working on the ceiling and on the wall that is drawn there that we are not paying attention to. We only want to talk about the forces working on the object. So, what's our number one force? Excellent. Okay, what else? Tension. All right, so we have tension working this way. I'm going to call that T for tension, capital T. You could do F little t, but the problem is I have a tension working in this direction. Now I'm drawing it from the center, but it's still the same angle. So this is tension, and we need to differentiate between the two. So what should I call this one? T1. Call this guy T2. Could you flip-flop it? Can I make this 1 and 2? Yeah, it doesn't matter. All right, so it just shows you that there's two different tension values. Now remember, vectors can move everywhere. So this box is being pulled in this direction, but I'm kind of looking at the center of mass and pulling it that way. Okay. What else do we know? If it's motionless. I've heard this from a few people. Why is there no normal force here? Because it's not lying on a surface. So a normal force, I also call it a surface force. It's just keeping you, the normal force is keeping you from falling through a surface. So you have to be touching something. And if we look here, this box is only attached to ropes. It's not attached to a surface. So we're not going to use the normal force here. Okay? When this is motionless, what do we know? Yeah. We're going to draw to actually figure that out. But what do we know because it's motionless? We know the net force is 0. Okay? So we know that the sum of the forces in both x and y direction have to be 0. So that's what I want to look at then. I want to look at, all right, what are the forces in the x direction? What are the forces in the y direction? And I know they have to be equal. Okay? So the opposite forces will be equal. So let's draw the free body diagram. So we'll just draw that here. So on the final, on the test, on any quizzes, if it asks for a free body diagram, you are just going to draw a sketch of the forces working on the object. And that's your answer for free body diagram. Now we're going to go a step further to set up some equations to get helpful information that's going to be able to help us solve based on what other information they would give us in the problem. So, you guys see we have the tension 2, so T2, and the gravitational force. See how they're perpendicular to each other? I'm purposely going to make that my X and Y axis direction. So I'm going to go straight up and down. Okay, and we don't know any of the values, so I'm purposely going to draw my T1 vector, because once I draw the vector, then I can easily draw the components. So I'm going to draw this way, not too big. And then I'm going to draw the X component here, and the Y component, leave that here. So this is T1Y. This is T1X, and this is T1. Another way we could have said F with a little t, that's another way to write the tension force. Alright, so we have the components, and now we have some XY components happening, okay? So now we can take a look at the X. So I have this X component of my tension. What is going to be the opposite force of my X component of my tension 1? It's going to be T2. And it's got to be equal and opposite. So it's going to be right around here. So this is T2. I should make this T1 here. All right, so that's T2, and I know that's going to be equal and opposite. So T2 equals the X component of T1. All right, and what do I know about T1Y component? It's opposite the gravitational force, and we're going to make those equal. So this is the gravitational force. So I know Fg equals T1Y component. All right, now let's take a little flashback into the last unit. In the last unit, we made T-charts of our X and Y motions of the parabolic motions, right? And we would do this, and we'd say, all right, we have delta Y, we have Vy naught, Vy, and so on. We'd have a Vx naught. And in the problem, I would say, oh, you know what? Your initial velocity is 20 meters per second, and that is at a 45-degree angle. What would we write for the y component of the initial velocity? 20 sine 45. The reason is we are taking the magnitude of the resultant vector times sine of the angle for the y component of the vector. For the x component, that would have been then 20 cosine 45. Well, guess what? That's what we're still doing. The component vectors work the same way. Even though now we're not with velocity, now we have forces, the components work exactly the same. So this T1x here, you guys, is actually T1, so this resultant vector, times the cosine of whatever this theta here is. All right, so it would be the theta value with the x-axis. So this T1y component is going to be what? T1 sine theta. So if I knew what T1 was, if I said, oh, T1 is 30 newtons and it is 20 degrees above the x-axis, then this would be 30 cosine 20. Did I say 20? Do you like how short-term memory? And then this would be 30 sine of 20. And then I would know what my T2 is, and I would know what my gravitational force was. Make sense? Okay, so we use the components. We're going to eventually set up equations, and then we can solve for the unknowns.